Good afternoon, everyone. I'm Catherine Sims, EXO's Manager of Membership Experience, and I'd like to thank you all for joining us today for this PowerTalk webinar hosted by ASCO Power Technologies by Schneider Electric. Today's session is titled Maximize Emergency Power Efficiency with Microgrid Interconnection Devices. And we're really excited to have two speakers with us. Victor Bonachea, Director of Product Strategy, and Adi Rawal, Product Owner of New Product Development. So with that, I'll turn it over to Victor and Adi to get us started.
All right. Thank you, Catherine. So we'll go to the next slide. I really appreciate everybody joining today. All right, so quick introduction of the speakers here. We have Victor, who is Director of Product Strategy and is an industry leader with 14 plus years of experience in standby power solutions and source management. And my name's Adi Rawal. I bring 8 years of experience in standby power systems and source management. Let's go to the next slide. Let's jump right into this. So what's on the agenda for today? We will be providing an introduction to microgrid interconnection devices, the definition, purpose, and the key characteristics, the NEC, National Electric Code updates, the application of these MIDs or microgrid interconnection devices, and a visual learning, which includes an animation of a single line diagram to illustrate how the inverter-based resources will power our loads. Finally, we'll have the next steps and resources from there. So what is a microgrid interconnection device? A microgrid interconnection device per the NEC is designed for emergency systems, isolating your primary service, which is your utility, and your non-essential loads to provide inverter-based emergency power. So what we have is our product source pack here. What we say is a source pack to a battery energy storage system is what an ATS is to a generator. We'll be talking more in the next slide about how these architectures are different. So next slide. So what you see on the left here is the one line that we know very, very well, right? It includes your utility and your generator and includes an automatic transfer switch. In most cases, when utility is acceptable, you have your utility powering up your loads. When utility goes out, utility fails, the automatic transfer switch goes to your generator source, right? But they are never in parallel. It's either utility feeding your loads or your generator feeding your loads. It's never both. Now let's go on to the right side, which is the new architectures that we have today with the microgrid interconnect devices or source pack, and how do we bring battery energy storage systems into the mix? What happens in this architecture is you have your utility source and your battery energy storage systems are connected in parallel with the battery energy storage systems charging or discharging, but they're both in parallel in an ideal scenario when utility is acceptable. When utility is not acceptable, what happens is the microgrid interconnection devices opens that breaker, isolates your utility, and lets the battery know that it will be providing all of the power to the loads. When utility comes back, what happens is it will make sure that it checks for the voltage frequencies and ensures that that breaker is closed, and you have your utility and your battery energy storage systems again running in parallel. So this architecture on the right has utility and your BESS systems connected, whereas on the left, which we are used to today, you have utility or your generator part of the architecture. So let's dive a little bit more deeper into it with the next slide. Your battery energy storage system use cases. The primary use cases are demand charge reduction, your time of use tariff management, also enabling renewable self-consumption. However, you can also use this for additional resilience and backup power for your loads. So in an event of an outage, the storage can be used to provide backup power with your battery energy storage systems with an inverter. Next slide. So how does a microgrid interconnect device actually operate? So as I was going through in the one line slide, right, is the controller for your source pack here will monitor your utility and your inverter based power. Upon your utility failure, the microgrid interconnection device or source pack acts as a grid isolation device. So it'll open up that breaker, separate your utility and non-essential loads from your emergency power. This is extremely important because you do not want to be backfeeding your utility and you want to be isolating it. Once the utility comes back, the controller detects the acceptability utility, lets the inverter know of this, and enables with a Form C contact, letting the inverter know which mode to be in. The inverter, the BESS system will ensure that it is in that grid form mode and we'll reconnect and we'll close that breaker to make sure the utility and your BESS systems are working in parallel now. The reason I have a Socomec BESS system there is the source pack is vendor agnostic. It uses a Form C contact to communicate with your BESS system, your inverter, to let it know which mode to operate in. We also, if you go to the next slide, click through. We do have a Schneider BESS as well, which would be compatible with this, but the source pack system is compatible with any BESS system that accepts a Form C contact. Next slide. So just going through the components of the source pack device here. The source pack device includes the controller, which monitors your sources. It includes communications with a Form C contact to indicate to utility and inverter-based power, along with which mode does the best backup power need to operate in. And it includes this motorized breaker, again, used for open and closing to isolate your utility source. It is listed to UL 3008 and approved for emergency systems. Today, this function is done by protective relays. This particular system that we have, the way the need is accomplished or the requirement is accomplished today is using protective relays and third-party solutions and cobbled together without a UL listing. And Victor will be talking more about that in his slides, but it's kind of cobbled together as a solution today, and a lot of additional testing and so on is required to get that system together. Whereas the source pack system is an integrated solution that comes right out of the box, ready to go. Let's go to the next slide here. Victor, over to you.
Thank you, Adi. So as Adi mentioned, the need for a device like SourcePact, which is known as a microgrid interconnect device, didn't come out of nowhere. The electrical market has been changing. It's been evolving over the years as we've seen more renewables and DERs, things such as solar, such as battery energy storage systems being used on the day-to-day, going from something we rarely saw to something much more common out there in the industry. And with that, the codes and standards have evolved with it as well. The first interesting thing that's changed over the last few code cycles in the National Electric Code, NFPA 70, is that in the past, the use of battery energy storage systems was, depending on which part of the code you're looking at, either restricted and not allowed or vague at best. But over the last few code cycles, it's become very clear and it's explicitly mentioned now, as you can see here in Article 700.12, that energy storage systems are now allowed to be used even for critical standby systems and emergency standby systems. Beyond that, they go to talk a little bit more about it. Not only do they say, hey, now you're allowed to use energy storage systems or BESS essentially as a standby power source for emergency applications. It goes on to say that you're allowed to operate them, and that's shown on the right-hand side in that excerpt. You're allowed to operate them in parallel with the normal source when everything's okay. And this goes back to some of the applications that Adi just mentioned, which is when people are putting in generators, yeah, sometimes they do peak shaving and things like that. But for the most part, its primary purpose is emergency standby power. But when people are putting in battery energy storage systems, they actually have various use cases in play. One, obviously, the emergency standby power, but the other really big one is going to be to help reduce your overall energy cost by doing things like playing with your energy rates and your time of use charges by charging when the power is cheap and discharging when the power is expensive, and maintaining a certain minimum capacity for your emergency standby applications. So by having this first change in the National Electric Code like I said, over the last few cycles, it's saying, hey, you're allowed to use these systems, and you're allowed to use them for more than just standby power. You're allowed to use them in parallel with the utility to help reduce your overall energy costs, which is a huge value prop to facility owners and designers out there, because now they're buying a capital piece of equipment, not just for standby power, but they're also buying it as a way to reduce their overall operating costs and expenses by lowering their energy expenses during the operation of that battery system. In multiple spots in the code, it goes ahead and reiterates the fact that you're allowed to use them in parallel um, with with your utility source when need be. But then the code starts to get a little bit more specific since you are using it as an emergency power source. How does it need to operate? How does it need to be treated when it's being used for that use case, right? So it goes on to state right here, you can see another excerpt from 712. The system shall isolate the emergency system from all non-emergency loads when the normal electric supply is interrupted. That's really the critical sentence in that piece. So what does that really mean? Well, when you're operating in parallel with your utility because you're using it to, again, subsidize your energy costs, whether it's a battery system or solar or whatever, you're going to be grid tie. You're going to be connected to the utility. Both your loads and your battery system is going to be synced up and producing power because you're pulling power from both utility and either reducing your overall energy from the utility by feeding your loads with a battery system, or if you have enough capacity, potentially even selling back to the utility if you have that kind of agreement with your local service provider. But it says when you're doing that, yeah, obviously you have to be grid connected. But when power goes out, you have to isolate before you bring your emergency system back online as a your battery energy storage system online as an emergency power system. And that's for a lot of the same reasons that we have to do that with a generator and a transfer switch. You don't want to backfeed the utility and potentially hurt someone who's working upstream to repair whatever caused the outage. Your battery system isn't going to be sized to feed power to the whole grid because essentially the grid is a power source, but when it goes down, it essentially becomes a load. So your system is going to try to feed power out onto those lines, and I can tell you, your battery system, unless it's utility scale, is not going to be able to handle that, and it's going to overload and potentially get damaged, or at the very least, the protective function is going to shut it down. So you need to have that isolation in place to kick in when an outage happens so that you can go from operating in a utility energy reduction mode, grid interactive mode, when everything's okay, to a grid forming emergency standby kind of mode of operation when the utility power fails. And this is all requirements of the National Electric Code. So they're saying that you're allowed to use battery systems. You're allowed to use them in parallel with utility when everything's okay. However, when power goes out, you have to go ahead and isolate your system. And now it takes it one step further and says, well, when you're doing your isolation, the equipment that's being used to do that isolation, as you can see in 702.5, and these are just some excerpts. There's similar wording in various aspects of Article 700, 701, 702. We just snapshotted a few of them. Over here it says, the equipment shall be suitable for the intended use and shall be listed, designed, and installed to prevent inadvertent interconnection. So the key important takeaway there is really saying that, well, the device that's doing this isolation has to be listed. Okay, well, that's not a foreign concept to anybody. That's the norm with transfer switches and generators. UL 1008 is usually the standard to make sure that they're being used for the right that they have the proper design and performance needed to do that job reliably and robustly. But the important part is for the intended use, meaning you can't take some other device that's UL listed to some other standard, for example, a circuit breaker listed to UL 49, and apply it into this application, because UL 49 is not a standard about isolation. It's a standard about overcurrent protection for molded case breakers. So you have to have your isolation device, it has to be listed, but it has to be listed for the application of isolation of DERs, basically. This here is a diagram of a microgrid interconnect device and how it should be applied in a system. And this is, again, another direct excerpt from National Electric Code. So over here, the microgrid interconnect device, which is what we're calling source backed, you can see that this is almost in line downstream of a primary switchboard. So you would have utility coming in, and you'll see more of this in more one-line diagrams coming up. You'll have utility coming in this case, somewhere to the right over here, right? It's feeding to a main board. Now that main board has a branch that's coming down that's called primary source that's going through that microgrid interconnect device. And over here we have a downstream, let's call it an emergency switchboard or a secondary board. And on here you have your DERs, so you have all your inverters connected to it, and you also have your other critical loads. So that when this device opens up, you are now islanded from your utility and your non-critical loads, and that these DERs can kick on, feed power to these AC loads over here on top of the microgrid interconnect device in the diagram, without having to worry about feeding back upstream to the non-critical loads or into the utility. And there's various aspects of the code that are referring to this, all kind of reiterating the concept that we discussed in the last couple of slides. Now, the question becomes, well, okay, there's a UL listing requirement, or a listing requirement at least. What do we list it to? So this is where it gets interesting, actually, as sometimes happens, the codes were actually ahead of the standard. So the National Electric Code had that requirement before a standard existed for it. However, since then, steps have been taken, and what's called a provisional standard, essentially, or an outline of investigation, has been created with UL, called UL 3008, which is specifically for automatic interconnection switches for use in emergency systems. So it's a standard that is actually it's an outline of investigation that's just been developed specifically for the application of isolation and microgrid interconnect devices. And it takes a lot of inspiration from other existing standards are out there. UL 49 from circuit breakers, UL 1008 from the ATS world, and it kind of combined aspects of both of those to get you the sequence of operations you need and the performance you need. So some of the noteworthy pieces around this is that, first of all, it's got all the performance requirements. The performance requirements are there to make sure the equipment will act reliably and robustly. And that inspiration, a lot of it came from UL 1008. The logic there was really that 1008 is to ensure that you have a robust transfer switch to help you activate your emergency standby system, both start the generator and transfer over to it. And if you're using a battery system with a isolation device in a backup system, why should the performance of that device be any less reliable than what you would expect from a generator and an ATS? It shouldn't be, right? It should be just as, if not more reliable. So it took a lot of inspiration from 1008 in that aspect. And that's where you see a lot of the test sequencing for the electrical performance of the unit coming into play. There's endurance testing with load, without load, overload levels to ensure the equipment will operate reliably for many, many cycles, even under conditions that are outside of its normal operating parameters, just to make sure it's robust enough in that sense, temperature rise, and things like that. But the interesting thing for this standard, unlike UL 1008, is that you actually have to do every single test twice. Once with the current flowing downstream and again flowing back upstream, since in this case, DERs could be used to sell power back to the utility, the current could actually be flowing in either direction. So you have to make sure that the equipment can perform reliably with current flowing in whichever direction it is at that point in time. And there are nuances to the product's designs and things like that, where that is actually a very critical design point because it impacts things like arcing and things like that. Then there's other pieces that have to do with operational tests and sequence testing. And a lot of that inspiration came from UL 489 because a transfer switch can actually not usually be used in applications like this. And the reason being, transfer switches require a good power source to transfer to the source it's going to. Because usually utility goes offline, you don't have the generator online yet, you bring the generator online, and once it's online, that's when you transfer and you energize the transfer switch's transfer mechanism, whether it's a motor or a solenoid, with generator power for it to go over. In this case, the isolation device has to isolate before the battery system can come back online. But if the utility is out and your battery system is still cannot come online yet as a backup power source, how do you do that? So you need a device that can store energy. So breakers are a device that with spring charge mechanisms in there can store energy in those springs and trip even when there's no source of power on the system. So breakers are often the key component in these types of devices, but they were tested a little bit more robustly than you would normally see in UL 49. So the operational side is inspired from 489, but the performance is still closer to UL 1008 on the ATS side. The reason being, with UL 49, when you're qualifying a molded case breaker for short circuit protection, every single test in the UL sequence, or most of the tests in the test sequence, are done on a brand new circuit breaker. It's a pristine breaker for going into every test. Meanwhile, with UL 1008 and transfer switches, you actually have to use the same exact sample for numerous tests. You don't start off with a pristine sample every single time, which makes it a much more difficult test to pass. So again, going back to the concept of at UL 3008 should not result in anything any less reliable than what we would expect from a UL 1008 transfer switch. It actually imposed that requirement on microgrid interconnect devices. So even though many of them are using molded case breakers, these are not just breakers to the 489 standard. These are breakers that were tested above and beyond what a standard UL 49 listing would accomplish and have proven that they can pass a UL 3008 test sequence, which is much more robust because it does not allow you to change out your samples for every test. So at the end of the day, you result with a standard that is taking inspiration from both ATS and breakers, but proving that you have a robust device that can perform that isolation function repeatedly and reliably when you have an outage. And again, it's going beyond that of a standard UL 49 breaker. That's why you can't just take any breaker and put it into this application, because not any breaker can pass the more advanced UL 3008 qualification. And here we have an example of a one-line diagram kind of showing a more detailed view of the National Electric Code example that I gave you before, so showing it in an actual system. Now, this is a one-line diagram from an actual project that's been implemented in the field. And what we can see here is that we have a utility transformer on the bottom left corner feeding up to this main board over here with some other non-critical loads. One of the branches coming off of there is going through an isolation device, which in this case is the microgrid interconnect device, or source pack as we call it, going to an emergency panel over here, which has some other loads on it, as well as going back to your DER. In this case, it's a battery energy storage system, 220 kilowatt hours of energy storage, 125 kW peak output. So you can kind of see where it fits in line in the system, so that you have your emergency system down here that becomes islanded during an outage. And then upstream over here, you have your non-emergency system that's not being backed up by that same inverter downstream over here. And we'll go through some diagrams in a little bit to show exactly how this operates in the full sequence of operation. So let's go through some of the architectures because we only showed one here out of the many that exist. So the first one and the one we've been using an example in the conversation so far has been what we would call a battery-only architecture. So over here, you have a utility feed coming into that main board, kind of just like the diagram we went through. It has some non-essential loads in it. Has a battery energy storage system. Sorry, has the interconnect device here feeding downstream to your essential loads on the emergency board, and over here you got your battery energy storage system into it. This is the simplest. The only backup power you have on it the is the BESS system. And really, if you're putting in a BESS for energy savings already, it's almost like a no-brainer to just throw in the interconnect device to enable the backup power ahead of time. Because it's such a minor cost relative to that of the battery energy storage system, right? So if you're spending hundreds of thousands of dollars already on these storage systems, the added cost to add an isolation device to enable that battery system to also serve as a backup source, not just for energy cost optimization, is almost a no-brainer. You can go over here to a slightly more complex application, and we're calling it battery and generator. In this case, you have both a generator and a BESS system being used for backup power. The way I like to think of this type of use case is for brownfield applications. You can imagine a line right here between the utility and the interconnect device over here, a vertical line. Everything to the left of the line, let's just call that an existing facility. So you have utility coming in, just like before. You have your non-essential loads. You have an ATS backing up an essential loads here with the generator. Let's imagine it's a school, for example, right? It's an existing school. Now, they want to expand the school. They want to build a new wing onto the school. And they also have some new green targets or some new requirements to be more sustainable. They can go ahead and design the new wing of the school without impacting or having to mess with any of the existing wiring in the old standby system. So the new wing, they can build it out, put in all their loads, and have it feed off the main switchboard coming into the facility. But when you put the microgrid interconnect device there, then you can put downstream of it, obviously the essential loads, but also that new solar generation and battery energy storage system, so that when utility goes out, your old building generator kicks on, ATS switches over, is being fed just like you would today, but your new wing will actually be backed up from the battery energy storage system. And this is nice because it minimizes impact to your existing infrastructure in the facility that you might already have in place for the ATS. And also, if you already have that generator size for the existing loads, you might not have the option to put more load on it either, right? So rather than have to replace the generator, get a bigger one, which might not be a viable option for someone on the market, they can go ahead and use a battery energy storage system and meet their targets and not necessarily have to throw away old existing infrastructure that's in place. So it's a nice one to help you scale a facility as well as to minimize the impact and intrusiveness into all the existing infrastructure and equipment that you have in place. And then the last one is battery first. So in battery first application, you start off with a utility coming in, feeding your non-essential loads on that main board, then going through your isolation device. Now downstream of the isolation device, you have your DERs feeding your essential loads, or let's call these essential loads 1 actually, or essential loads 2. And then downstream of that, you have an ATS that's connected to a generator feeding your essential loads 1. And the main idea behind this one is a couple different pieces. One is most outages out there tend to be less than 20 minutes. So why don't you minimize the runtime on your generator to save maintenance and fuel and all that, as well as potentially get a smaller generator to help you save on your expense of the generator itself by only putting your most critical loads that you have to keep online during an extended outage. So the way this would work is utility would go out, your isolation device would open up, your DERs would now be providing standby power to these essential loads 2 and essential loads 1 downstream. Now the ATS is seeing power coming into its preferred source from the DERs, which it doesn't differentiate between utility or battery. So it doesn't start the generator or transfer just yet. But if these batteries start to get low, they can send a low battery signal, or if they just fail for any reason, that would be detected by the ATS, and then the ATS would go ahead, start the generator, and transfer over. So in many outages, you can actually go ahead and keep both sets of loads online without having to even start the generator at all. So this gives you a very sustainable way to kind of minimize emissions, um, and minimize the size of your generator only for the situation that you truly have an extended outage and you have some priority one load that must not go off. So over here are kind of things you want to keep online, but you don't have to. Here are things that you must keep online. If you want to think about it almost like equipment loads and critical loads and things like that, or even for non-critical applications. So let's go ahead and step through a full sequence in a little bit more detail. So over here, I have a battery plus generator architecture, just like I showed you a few minutes ago. And we can see the utility power coming in on the bottom left here, feeding through a main board. Off of that main board, you have some existing infrastructure that is feeding essential loads over here that's backed up by a generator and ATS. The other branch coming off of it is going through the interconnect device, which has some essential loads being fed off of it downstream on an emergency switchboard there. It also has two DERs on it. It's got solar, it's got BESS. When everything is good, everything's hunky-dory, the essential loads over here on the left are connected to utility power, just like your spec generators offline. Microgrid interconnect device is closed. And the power is being fed from BESS and solar in a grid interactive or grid synchronized mode, meaning that that power is coming out and feeding these essential loads, potentially feeding upstream through the interconnect device to the non-essential loads so that you're using your own power rather than utilities power. That's saving you money in the long run. And if you have the type of agreement in place, it would be feeding upstream out to the utility and potentially backselling and earning you credits. But what happens when the utility power fails? Well, utility power is going to go ahead and fail. Obviously, everything's going to go dark at first. And your inverters on your DERs are going to shut down. That is a requirement of the design of these types of grid interactive inverters. Excuse me. That when they do not have a good anchor resource or a source to synchronize to, they must shut down so that they are not producing power out of spec or dangerously backfeeding the system or anything like that. So just because you have the inverters in place, if you don't have the right isolation, if you don't have a good power source, you don't inherently have the backup power without the microgrid interconnect device, which is the whole point of this. It enables you to turn those back on, not in a grid tied, grid connected mode, allows you to feed it a signal to switch it to grid forming mode, which we're about to see. So like I said, those inverters shut down, so you're completely in the dark. You got no power to operate your transfer switch until the generator comes on. But you do have enough power for the microgrid interconnect device over here because it's got a stored energy device, a spring mechanism in that breaker to trip open, which means that this emergency system over here, the one with the BESS, is now in its own private island and separated from the rest of the system. You can see that the solar, the BESS, and these essential loads are now completely segregated downstream because this guy's open from this part of the system. At the same time, your ATS does what an ATS does, detects the outage and sends a start signal to the generator. Now, at the same time, I kind of skipped over it because it happened very quickly in the animation. When this guy opened, it went ahead and sent a signal up. And let me go back for a second just so you guys can see it again. If I click over it, you'll see this guy sent a signal up to the BESS. Now, that's a signal that tells the battery energy storage system, hey, I've isolated, I'm open. It's okay for you to go from grid interactive mode to grid forming mode. So like I said before, it's usually producing power in parallel. That's one mode of operation for these inverters. The other one is grid forming. So when this isolates, it sends a signal, which is just a form C dry contact, up to the BESS telling it, hey, you can switch over to grid forming mode, which means start producing power. You don't need an anchor resource, and you're not worried about backfeeding. When it receives that signal, the BESS system will kick back on and start producing power in that islanded mode now, in that grid forming mode. And at the same time, the ATS is doing over here what the ATS always does, which is start the generator. Generator's online. It detects the generator power and transfers over to generator. So now both sets of essential loads are good. They're both being fed from their respective backup power source, be it the DER because you're isolated now, or the generator because you went ahead and transferred over. Utility comes back. We wait some time. There's time delays on both the ATS, of course, and the microgrid interconnect device to ensure the power has stabilized and has truly returned. but they each also have their own upstream sensing that is monitoring that continuously to reset that timer as needed. But once it sees that power has come back and is stable for a while, it goes ahead and sends us the microgrid interconnect device sends a signal up to the BESS, telling the BESS, hey, I want you to go back to grid synchronized mode of operation. So it very momentarily shuts down because now it's back in grid sync mode. But since this is open still, it cannot see that utility power yet. The inverter cannot because it's not being fed downstream yet. So it momentarily opens. It stays open and momentarily shuts down over here. Once the microgrid interconnect device detects that it's a dead bus and it's safe to reclose, it goes ahead and closes that breaker again. So now all of a sudden you got utility power restored to downstream of your system. Your ATS transfers as well. And once that power is restored over there, the inverters can go ahead and detect that and restore grid interactive performance, meaning that breaker reclosed, we're feeding power downstream, inverters are in grid sync mode, grid interactive, they sync back up to that utility and start producing power in parallel again, which helps you reduce energy costs overall. And that's the overall sequence of a microgrid interconnect device, as well as an ATS, which was not the focus today, but you can see how they can both simultaneously exist in a system at the same time. And this is just one of many applications in which you can see that set up. You saw before there's a battery first applications as well. You can see it architected like that. And even though I only showed those 3 key architectures, there are many, many more, all really unique and dependent on what your use cases are and your application is at your site. So with that, I'll give it back to Adi.
All right, thank you, Victor. So coming back to, as Victor explained, the microgrid interconnect devices and the role they play, SourcePact is the offer from ASCO, and it's focused on the CNI segments, which are commercial and light industrial segments. So think about your commercial buildings, the school example that Victor gave, the warehouse light manufacturing. And the battery energy storage systems are between 100 to 500 kW are typical in these segments, with common voltages being 480 volts and 208 volts. So this goes directly into our next slide for the product offering that exists for SourcePact, which is right here, right? So we have a 480 volt system configuration available, as well as 208 volts. And these are also available in terms of 600 amps and 800 amps. It's a type 3R outdoor enclosure that's available with top and bottom cable entry. Again, like I had talked about before, it uses the form C contact to let the inverter BESS system know to go either into grid tie versus grid form mode. So let's keep moving into the next slide. So I'll be talking a little bit more about the intelligent switchgear. So as you see here in your one line, you have SourcePact there in the one line. That is a component that plays a part in the overall microgrid story to bring your best part of your system architecture. There are other Schneider offers available to help as a system solution to offer that. You have the EMA and the EMO, which are offers which are EcoStruxure Microgrid Advisor and the EcoStruxure Microgrid Operator that help with maximizing your best capacity. Adding things like load management and so on into the mix to really maximize your best capacity there. There's also the panel boards and the energy control centers available here as well. So here's just a one line to show that there is the component piece to it, as well as the system piece to it. So yeah, let's go to the next slide there. You have the best offering from Schneider, which has a small and a medium offering. The small is up to 180 kW, and the medium is 500 kW. These offers are both UL 9540 certified and are available for order. Let's go to the next slide here. This is just showing, like I talked about in the one line, right? From a system view perspective, a system solution is available, and SourcePack plays a part in the overall solution. SourcePack is vendor agnostic, so can be used with any best system and inverter system. But the intelligence with a Schneider Best that is offered, the advantage is having the microgrid operator and the microgrid advisor to really help you, again, maximize what the best can offer as a emergency backup solution. So let's go to the next slide, which is coming towards the end, right? So these are the resources that you have available. You can scan these. These are resources available for your SourcePack solution, right? From your brochures, data sheets, drawings, technical bulletins, and your manuals. We will be sending this out after the fact, so you guys can click on those links, but those QR codes would work as well. And going towards the last slide here is there is the overall website there, the ASCO Power website, which will include all of the updated information on SourcePack and again, additional white papers and so on microgrid interconnection devices to kind of find out more information about those.